see this, aren't you? There we go. It'll fire up in just a minute, okay? I'll just start writing down here. So 2.5, this is going to be on continuity. So our first question you guys asked was number 13, but I guess before I get to that particular question, what I'd like to do is just look at an image and talk about a couple different kinds of continuities and the difference between their naming. Because we have two different things. We have what's called a jump discontinuity and what's called a removable discontinuity. Now we talked a lot about these kind of discontinuities in pre-calculus, but let's talk about them now in calculus. So just kind of focusing in on this. I'm just going to kind of look at number 1 and number 4, because these are two different types. So number 1 has you guys agree that there's a discontinuity at x equals 2? Now when we talk about discontinuities, we talk about the x values for which these things happen. Because sometimes, sometimes the y value is in the same location. It looks like the y value is about 1 there. You guys agree? So it has a limit of about 1. But if you look over here, what y value would you choose? Would you choose the y value at 0, or would you choose the y value at 3/2? So that's why we don't identify the y values, because it's possibly two different ones. So we just say, we're at what part of the domain does this happen? So this has a discontinuity at x equals 2, because there's a removable discontinuity. The reason why I call it removable is it looks like I took a point and removed it. Okay. Now this over here would be a jump discontinuity. Now this discontinuity happening clearly because this is a piecewise function, right? It's one line right here, and then it's a different line with a different y-intercept and slope right here, isn't it? And those two lines don't connect. So that's why they call it jumps, because it hops from this point to this point and jumps. Like an asymptote, I'd consider kind of a jump discontinuity as well. Well, when they move in opposite directions, for sure, like if it's up and then down. But it's like, so an asymptote is another type of discontinuity. But these are the main two types. You have your removable, and then they say these are non-removable, but they also use the word jump in here. Okay, so if you guys want to say jump discontinuity instead of not removable discontinuity, you're welcome to use jump, because it's a lot less letters. Okay, you don't know what you guys are talking about. They've already defined it, so we can use it. So that's what they look like. Now you guys asked some questions as far as the expressions, like how do I take it from expression form to determine this discontinuity. So number 13 gives me a function that says 1 over x minus 2 minus 3x. So what I have is I have the subtraction of two functions, right? And what I know is the subtraction of two continuous functions are continuous, right? Except this function right here, this 1 over x minus 2 is not continuous, is it? Where's its discontinuity? Yeah, x equals 2. So it's x equals 2, and what kind of discontinuity is this? Is this a removable, or is this an asymptote? Does the x minus 2 cancel? No, so that means it's an asymptote. Does that make sense? If it cancels, it's a whole or removable discontinuity. If it doesn't cancel, it's an asymptote. Now I know asymptotes are in section 2.6 and in 2.5, but we might as well talk about it now because we covered those sections last time. So this has an asymptote at x equals 2. Is that clear? Okay. So that means I think what they're asking for is they want to know at what point do these things fail to be continuous? So it fails to be continuous at x equals 2. Note, the domain of this function is minus infinity to 2 union 2 to infinity, right? Notice that there's your whole, not your whole, but your asymptote. There's your discontinuity. Now, where it's continuous and where it's domain are not exactly the same things, but they are related to each other. Does that make sense? So if you look at the picture, the very first one, the domain of this thing would be -1, open to 2, open 2, close 3, right? So its discontinuity is at 2 because it's not part of the domain, right? But this right here, the number 4, it's got a discontinuity at x equals 1. But x equals 1 is part of the domain. The domain goes from -1 to 3, doesn't it? So the domain and its continuity are not exactly the same. Where it's continuous is a subset of that domain. But your domain can give you, like, you guys agree that your domain can give you places where it's discontinuous? So that's why a lot of these things, we're just checking the domain. What else does it say? Oh, this is a non-removable, right? It's not removable because it's an asymptote. It's not a hole, it's an asymptote. Because it's an asymptote. Number 17.
Excuse me.
Yes, sir.
You need help understanding 5 and 6.
Yeah, let's do that. So before we move on, then 5 and 6.
I mean 5 and 7.
5 and 7.
So we don't do.
Well, good. Well, let's do that right now because the pictures are useful. So then we can take the pictures to these expressions. Okay. So number 5. What we have to do is we have to look at this particular function. Then I'm going to ask some questions about this. Try to see if I can fit it all in at once. Probably not. Whatever. Okay. So this function right here, it's going to ask. I'm going to do number 5, and I think 7. Good. 7 small. So number 5, it says, does f of -1 exist for 5a? So what I'm going to look at is I'm going to look at -1. Does -1 exist? Yeah, f of -1 is equal to what?
0.
0, because this is the point -1, 0. It is a point there, isn't it? So it's a close point. Letter B. How about the limit as I approach -1 from the positive side? Does that exist? So can I approach -1 from this direction? From the. Yep. So, can I approach, does the limit as x approaches this 1 of f of x equal f of -1? Do they approach the same spot? Do they both go to 0? So is it continuous? Yes. Remember, the reason why it's continuous here is because this is only going to be continuous from the right. Does that make sense? There's no function over here. So when I'm trying to figure out that, remember the 3 rules? When we look at the rules here, I'm going to kind of go back to the rules. So if we remember, for continuity, to be continuous, number 1 says that f of c must exist, right? 2 says the limit as x approaches c of f of x must exist. And if both of those exist, the last thing you have to check is, are these 2 values the same? You know, if this has to equal this. Does that make sense? Now, what this little notation is actually talking about a function from both sides, right? Because do you see any direction here on this limit? So if there's no direction on this limit, what direction are they talking about?
Both.
Both, right? For a limit to exist, it must be the same from both sides, right? But what if I have a left endpoint? What's the only direction I can come from?
The right.
The right. So that means this thing must be adjusted. You can only come from the right. Is that clear? So that means this only needs to be true from the right.
I mean, it's a plus, isn't it?
Ah, you're right. You're right. That's what I meant. Just checking to see if you're paying attention. I'm not.
Can we do,
We'll get there. 9, 2? Yes.
yeah, because
So, is that clear that this is continuous at x equals -1? Because it satisfies this, because it's a left endpoint. If it was a right endpoint, instead of having pluses, you'd have to have what? Minuses. Well, take a look at 3. Is it continuous at 3? No, because it doesn't exist at 3. Is that clear? Does that make sense? Okay. Number 7 says, is f defined at 2? So I'll just kind of show you. I'm just going to say it out loud. So what we're going to ask is f defined at x equals 2. And then B, it says, is f continuous at x equals 2? And then we're going to see if it's true or not. So at x equals 2, is it defined at... I'd prefer to look at... Number 6 is a better question. But we'll talk about it right now. Is it defined at 2? No. So is it continuous at 2? No, it fails number 1, doesn't it? Okay, let's look at number 6. That's a better one. Number 6 says, is f of 1, does f of 1 exist? Yeah, it's this point right here, isn't it? It does exist, and it's equal to what? When you plug in 1, you get what back? 1. Okay, so it does exist. Does the limit exist?
no.
Yes, because from the left it goes to what? Remember, when you're talking about limit, we're talking about close, right? So from the left it's going to what y value? From the right it's going to what y value? Okay.
It
So
doesn't say plus or minus.
So right now we're talking about both, right? So I'm getting rid of the direction. Is that clear? So far, yes, it exists. F of 1 is equal to 1, right?
But there's two places where it's 1.
We get there. Number 2 says
1, and
the limit x approaches 1 of f of x is also equal to, well, is equal to what? 2. So it does exist. That's correct, right? But lastly, did this one work? No, because this is 1 and this is 2, isn't it? It's got to be the same to it's got to be the same to be continuous. And remember, kind of like the layman's term of continuity is, can I draw this picture without lifting my pencil? No, I have to lift it at x equals 1, don't I? And for that to happen, one of these have to happen. No, I'm sorry, I didn't mean to interrupt you, but how's that a roll?
Sorry.
What's up?
But yeah, but isn't there not a limit because there's two places where you get 1 and 2? There's no.
Well, when we talk about a limit, we talk about driving to that point, right? So we only talk about close to that point. So as I get really, really close to 1, I'm getting really, really close to 2, right? So I'm on this road and I'm getting close to 2, aren't I? The limit doesn't care about when you get there, right? It cares about only when you're close. Same thing from this direction.
1, 1.
Well, there's no road to get there, right? It's just
That doesn't screw up.
it doesn't, because it's its own little island. There's no driving there, is there?
Right.
Okay. All right. So number 9 says, number 9 says we know that this thing is discontinuous at 2, right? So what value should be assigned to f of 2 so that we can extend the function to be continuous at x equals 2? You guys agree that this is not defined at x equals 2? What point do I have to plug in to make this defined at x equals 2? X equals 2, comma, 0. So what you could do is you could, like this piecewise function up here. Do you see how they inserted the point 1, comma 1 here? See that third line? That's just inserting a point 1, comma 1. You could just add a line to your piecewise function to insert the point 2, comma 0. And that would continuously extend it. All right, so 17. 17, we have the function f of x is equal to the absolute value of x minus 1 plus the sine of x. All right, so I told you guys to be careful of piecewise functions, right? And what we know is the absolute values are piecewise functions. Now, absolute values are nice piecewise functions because they're continuous piecewise functions. So if I just kind of, if you look at y is equal to just the absolute value of x minus 1. If I do a graph of this particular function, what this is this is the absolute value of x just shifted right 1 unit. So remember, the absolute value of x looks like a v, doesn't it? So the absolute value of x minus 1 looks like this. It's the absolute value function shifted to the right 1 unit. Do you notice how this thing is continuous at its break? Because what I know is it's negative x minus 1 on this side, and it's positive x minus 1 on this side, right? That's what absolute values do. They're negative when it's below this one, and it's going to be positive when it's above this one. And if you plug in x equals 1, you're going to get what in both places? 0. You're going to get 0 in both times. So this is a continuous function, isn't it? Okay. So back to the rules. The sum of continuous functions are, and how do you know the sine's continuous? Because it looks like that, right? So the sine function is a continuous function. So, yeah, I missed it. It should be right there. That's where the actual axis is. Is that clear? So the sum of continuous functions are continuous. Continuous plus continuous equals continuous.
If it's a minus continuous.
Still continuous. What if it's a times?
Continuous.
What if it's a division?
Continuous.
Except if the bottom is 0. Okay, so there are functions where it'll never be 0, right? Like I can divide, like if I have the absolute value of x minus 1, I can divide it by e to the x. Those things are continuous, right? Absolute value function is continuous. E to the x is continuous. And if you look at the graph of e to the x, does it ever touch 0? No. So that's still a continuous function because the bottom is never 0, right? 23. Oh, this is a good one. I know what their answer is in the back, but I'm going to give you the one that's correct. So, 23, right? Yeah. 23 says y is equal to x times the tangent of x, all divided by x squared plus 1. All right, so back to our rules. So if I'm just looking at the numerator, if these are both continuous functions, then the product will be continuous functions, right? So I really just have to look at the points for which each are discontinuous separately. Is that clear? Now I know y equals x is a continuous function. If you look at y equals x, it looks like this. Continuous everywhere, right? But what about y equals the sine of x? Oh, God. What if y equals, y equals the tangent of x? When we had to graph this function, remember that this is equal to the tangent of x is a ratio function, right? Sine of x over cosine of x. Is the bottom ever equal to 0? Yeah, it's equal to 0. How many times is the cosine equal to 0? Well, twice in 2 pi, right? So if you look at a unit circle, where's the cosine equal to 0? Well, it's equal to 0 here, right? And it's also equal to 0 here, right? But how many times do you go around the circle? A lot. Remember the cosine, when I asked you guys to graph a cosine function or a tangent function, I was only asking you guys to graph it in one 2 pi interval, right? From 0 to 2 pi. And the reason why I said you only have to do one cycle is because it just keeps repeating itself over and over again, right? So if you look at the cosine function, your cosine function does this. Sorry, this is no longer the tangent function. We'll get there. This will be y equals the cosine of x. And then we'll get to the tangent function in a second. So it's this one, right? That's the cosine function. So I know that it's equal to 0. If we're just going to go from 0 to 2 pi, it should be 0 to 2 pi. We can see that it's 0. It's 0 at pi over 2. It's also 0 at 3 pi over 2. So it's 0 here at pi over 2. It's 0 here at 3 pi over 2. You also know that this would be negative pi over 2. This would be negative 3 pi over 2. And can you tell the distance between these things is, what's the difference between minus pi over 2 and pi over 2? Yeah, they differ by pi, right? This distance right here is pi over 2, right? And this distance here would also be pi over 2. So pi over 2 plus pi over 2 would be 2 pi over 2. So that distance between these things happens to be pi. All right, so back to y equals the tangent. Y equals the tangent of x. Well, this is equal to the sine of x over the cosine of x. So I know that this function is going to be undefined when the cosine is equal to 0. So at pi over 2, it's not defined, and at minus pi over 2, it's also not defined. So remember, does this cosine cancel? So if it doesn't cancel, what am I looking at? Am I looking at a whole or an asymptote? So we're going to asymptote here. Sorry, the sound effects help. So now, what we know is the tangent function looks like this, doesn't it? Is that clear? But it repeats itself over and over and over again. So there's another one over here, and there's another one over here, and another one over here, and so on, right? Over and over and over again. So it's going to have a bunch of asymptotes, right? And every one of these asymptotes differ by pi. So this is going to be 3 pi over 2, next is going to be 5 pi over 2, next is going to be 7 pi over 2, and so on. So what I know is x is not going to be allowed to be equal to pi over 2 plus all multiples of pi, right? So when n equals, so remember what this actually means. So this is supposed to be like ... minus pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and a heck of a lot more, right? So what this means is this little formula here is just a quick notation to say an infinite amount of points. So when n equals 0, you get this one, right? When n equals negative 1, you get the one before. When n equals 2, you get this one, n equals 3, n equals 4, and so on. So this is where it's not defined. Does that make sense? What's that? Yeah, you can write it below it. You can write it this way as well. This would work as well. That's fine. So, well, we're not done. That's discontinuous at those points, right? Is there any place that I have to worry about? Dividing by what? X squared plus 1 is not allowed to be? Okay, let's check. So I'm all over. Let me zoom out. I got like a hot mess going on. So now we also have to check to see if x squared plus 1 is also not allowed to be 0 because it's in the denominator. So if you solve this, you're going to get x squared is equal to negative 1. So x is going to be equal to plus or minus the square root of negative 1, right? What's the square root of negative 1?
1.
Yeah, do you see I on this axis? No, so it's never equal to 0, is it?
Right.
Now you can kind of think about it this way. If you have y is equal to x squared, it's this, isn't it? And it never touches the x-axis, so it's always positive. So the spot where this thing is discontinuous is only at the tangent part of it. And that is right here. So this is your answer. You can either use the top line or the bottom line, okay? Those are the points where it's discontinuous. Did you guys ask 29? Good. Okay, so 29. G of x is equal to x squared minus x minus 6 all over x minus 3 when x is not allowed to be 3. And it's equal to 5 when x is equal to 3. How would I determine if that function is continuous? Yeah. Well, it can't be equal to 5 at 3, right?
Yeah.
But you're on the right path, isn't it? Well, how do you check for continuity? What are the tests? Continuous. Test. Step 1 says that f of what x value am I looking at?
3.
F of 3 has to exist, right? All right, let's check it. What is f of 3 equal to?
5.
Yeah, because when it's 3, it's 5. So this is just a point 3 comma 5, right? Number 2, the limit as x approaches 3 of f of x must exist, right? Well, we have to look. What function am I going to use? So if I'm asking for a limit, do I care about when I'm on the point 3 or just close to the 3? So what am I going to use? Top or bottom function? Top function, okay. So this is going to be the limit as x approaches 3 of x squared minus x minus 6 all over x minus 3. And how do you do this limit? What do you have to do? Yeah, I got to simplify it. So x minus 3 times x plus 2 all over x minus 3. Those will cancel. So this is going to be the limit as x approaches 3 of x plus 2. Can I plug in 3 now?
Yeah.
3 plus 2 is?
5.
5.
Yeah.
Oh, whatever. That's now number 3. What's the last thing that has to happen? The limit as x approaches 3 of f of x has to be equal to f of 3, right? What's the limit? What's the evaluation? So is this continuous?
Yeah.
Yes. Check, 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 right? All right, graphically what happened here? Sure. So graphically what we have here is what this function is, like this function other than 3, this thing simplifies to this it simplifies to that simpler to that expression there. Where is the green? Found it. We're looking, I found it. So I know that this function right here, which is this function, simplifies to this x plus 2, right? So what I know is that thing graphs just like x plus 2, except it's got a hole at 3, right? Why do I know it's a hole and not an asymptote? Because it canceled. That's right. Yep. So x equals 3, we have a hole. So 1, 2, 3, x equals 3. And I know that the y value is 5 because that's its limit. You guys agree? So it's got a hole at 3 comma 5. That's really what that means. It's got a y-intercept of 2. So it's going to look like this. So that is y is equal to x squared minus x minus 6 all over to x minus 3, right? What is, that's the new in red. What does this represent? 3, 5. Yeah, the point 3, 5, right? Where does that point have to live so that this function is continuous?
Right there.
Right on 3 comma 5, right? Right on this 3 comma 5. What if this was 4? Would this be continuous? No, it would be too low, right? So that's what we did, is you take a function that has a hole, and this little bottom part is a continuous extension. All you did is fill the hole.
So you allow a hole to exist when you fill it.
That's right, yep. Clever, isn't it?
Why?
Because you can.
I know, but it seems pointless.
Imagine
It
throw a
just
dot in
seems-
there.
That's right.
It's better.
It does.
Throwing a Band-Aid on it.
It's exactly what it is, yep.
It just seems like a waste of time to say that there's a hole in there just to put a Band-Aid over it.
Well, it really reinforces what it means to be continuous. That the function has to exist, the limit has to exist, and they have to be the same spot. So that all that is a engineered special case aversion, right? That's a mathematical problem for you guys to say, why does this work and why does something else doesn't? So, it's engineered for meaning, not just for use. It's like, hey, you kind of get this now. Because there are spots, like, there are things that in the real world where you simply just can't plug stuff in, right? But sometimes you can fix it. You can kind of introduce an outside force to make that work, right? So, 37 you asked? 37 says... Can we find the limits? It's a weird one. 19 minus 3 secant 2t. Well, what am I first going to check?
Zero can be funny.
Yeah, I just want to know if the bottom is 0, if the top is, if you plug in 0, right? Actually, we have to be careful. We have a radical here, right? And I have a denominator. So one thing is what's underneath the denominator can't be equal to 0, and another thing, what's in the radicand has to be positive, right? Sorry, not negative. It can be 0. Well, it can't be 0 because I guess the division as well. So actually the entire thing has to, this radicand has to be non-negative. So let's just plug it in. So what is the cosine of pi all over the square root of 19 minus 3? You guys agree the secant of 2 pi is 1 over the cosine of 2t? My bad. The secant of 2t is 1 over the cosine of 2t. So this is the same thing as 1 over the cosine of 2t. But what's t in this case? Yeah, 0. So 2 times 0. And then we kind of go through it. What's the cosine of 0?
0.
Cosine of 0 is
Oh,
1. So this is going to be 1 over 1, right? So this entire thing becomes 1, doesn't it? And what's 3 times 1?
3,
What's 19 minus 3?
16,
And what's the square root of 16?
4.
You guys agree it simplifies to that? What's the cosine of pi over 4? Root 2 over 2. It's this one, right? Root 2 over 2. Is that clear? I got it. 39's better. We're gonna actually, let's do I want to make one up that's kind of similar to 39. So I'm just gonna do kind of an example. So what about the limits as x approaches 0 from the positive direction of the cosine of 7, it's silly, of pi e to the square root of x. What if I ask something like this? I know it's really close as 39. It's almost as close as you can get, but at least it's a good question. To be honest, this really should be a two-part question, and 39 should be a two-part question. They should ask the limit from both directions because they don't do that enough when it comes to radicals. I will. That's why I was on your quiz. So let's talk about this. Where's the only spot where a discontinuity could possibly happen? Do you see any divisions?
No.
Do you see any square roots?
Yes.
What's under the radical has to be what? Yeah, greater than or equal to 0. You guys agree?
Mm-hmm.
So it's really this thing right here is the only spot, because remember that root x is a continuous function in its domain, right? E to the x is a continuous function everywhere, right? So its composite is going to be a continuous function well on the domain of e to the x. It's going to be the intersection of those two domains, right? When you multiply it by a constant multiple, domain still is 0 to infinity. Cosine of that thing, a composition, again, is the domain is going to be 0 to infinity. So I know the domain of this thing is going to be 0 to infinity, right? Which means I can plug in 0. You guys agree?
Mm-hmm.
But more importantly, I can plug in 0 as long as it's from the positive direction, right? Okay, so I can plug in 0 because it's from the positive direction. So this would be the cosine of pi e squared to 0. So this is going to be the cosine of pi e to the, well, what's e to the 0? 1. So it's just pi, right? And the cosine of pi is negative 1. Okay. What about this one? Can I plug it from the negative direction?
No.
No, it's outside the domain, right? There's no train tracks to get there. Is that clear? Like, whatever this function looks like, I know it is at 0. Who knows? I'm just going to give it kind of a radical looking thing here. Ah, love it? Okay, so the domain looks something like, who knows what it looks like? I'm not graphing it, but it's got to be something like that, right? Oh, I screwed that up. It goes down to negative 1, doesn't it? Like the y value is negative 1. I got the y value landing at 0, don't I? So technically it'd be that. Is that clear? Okay, so it looks like that. So I can come from the right, but can I come from the left? No, so this does not exist in this case. Clear? Is there another one? All right, so define g of 3 in a way that, okay. I'm doing 42. You guys can do 41. So 42, it says that we're given a function h of t is equal to t squared plus 3t minus 10 all over t minus 2. And what I need to do is I want to extend the function to be continuous at x equals 2. That's what I want to do. What can you guys tell me about this function here? Is it continuous at, sorry, not x equals 2, but t equals 2. Is it continuous at 2? No, because if you plug in 2, you're going to get something over 0, right? Actually, are you going to get 0 over 0? Did you guys check it? Because if you get 0 over 0, I bet you it's a hole. I bet you I can fix it. It is 0 over 0. So that means the top has a factor of t minus 2, doesn't it? Does that make sense? So the question is this, is I need to extend this thing in such a way, so make it a piecewise function. It's going to be t squared plus 3t minus 10 all over t minus 2, when t is not allowed to be 2. But at t equals 2, I need to figure out its value. Does that make sense? I need to find a to make that work. So we just go through the continuity test, right? Number 1, h of 2 has to exist, right? But what is h of 2?
We don't know.
I do.
A.
It's a, right? So it does exist. It's equal to a, isn't it? You guys see this is just, remember we just did this problem? It's right here, right? Like we just did it. We just did a problem that looks just like it. I lost it somewhere. Here it is, right? They gave us the value, right? We just had to check to make sure it works. Well, what if I put a variable in here? Can you still make it happen?
You can still try.
Oh, we sure can, right? So let's see. So the number 1 works, right? H of 2 is equal to a, isn't it? So when I plug in 2, I get a back. Number 2, its limit has to exist, right? What's the limit as t approaches 2 of h of t? What function do you use for the limit, the top or the bottom? So this is going to be the limit as t approaches 2 of t squared plus 3t minus 10 all over t minus 2. So limit as t goes to 2 of t minus 2 times t plus 3. Is it the same number?
It's not 3.
Oh, it's 5, isn't it?
Yeah.
It's 5 and 2. Thank you, that's better. T plus 5, t minus 2. Love it. So this is going to be equal to the limit as t approaches 2 of t plus 5. When you plug in 2, what do you get?
7.
7. Okay. Number 3 says that these two values have to be
Equal.
equal. So that means h of 2 has to be equal to the limit as t approaches 2 of h of t, right? The left-hand side is equal to 2, and the left-hand side is equal to a, right? So that should say 2. And the right-hand side is equal to 7, isn't it? So a equals 7, that's our answer. I'm going to give you guys a problem on a test like that, okay? Be ready for that. I'm going to give you 2 of them. One I'm going to give you with a removable discontinuity, and the other one I'm going to give you a piecewise this way and a piecewise this way. And there's slopes. One will have a slope of a or something. You're just going to have to make sure that they, instead of them doing like this, you have to make sure that you make them touch. Okay. So one to practice would be, like 45 would be a great one to practice. I'm not going to do it in class. You guys can try it. If you struggle, come see me. But it's the same thing. It's the same 1, 2, 3 step in all those. All right. Remember, but for like if I was going to do 45, the step that would work for this is the limit would have to exist, right? So that means the limit from the left, which would be this function, right? At x equals 3, would have to be equal to the limit from the right, which would be this function at t equals 3, right? Does that make sense? Those two things would have to be equal, right? So when you plug in x equals 3 here and x equals 3 here, they better be the same number, right? And that'll tell you how to find a. So it's in step 2 that you find a as opposed to all of them.